Hello, my dear students. In this class, I am going to discuss crystal field stabilization energy of coordination compounds. In the previous class, we understood crystal field splitting of coordination complex, and we also studied high spin and low spin complex. If you really understood the high spin and low spin complex, it's very easy to know and calculate crystal field stabilization energy of various coordination complex. So before going to do that, you must know the meaning of crystal field stabilization energy. You know how crystal field splitting takes place when ligand approaching the central metal atom, and we studied these splitting pattern in three complexes like octahedral, tetrahedral and square planar complexes. We also understood the reason behind the splitting, and after splitting the energy gap between Eg and 2Tg level is called as crystal field stabilization energy. So here the name itself indicates is a stabilization energy. So why it is stabilizing and what is the factor which is influences for stability? So stability means the one which is possessing less energy. So here after splitting, if electron enter to lower energy orbital, then the stability increases. So that's why it is defined as the decrease in energy achieved by preferential filling of electron in lower d orbital is called as crystal field stabilization energy. That means if the energy is negative, it indicates it possesses less energy. So less energy is highly stable. So the stability arises due to accommodation of electron into lower orbital after splitting. So that's why this is defined as the decrease in energy achieved by the filling of electron in lower d orbital of a splitted d level is called as crystal field stabilization energy. So it can be calculated by using a formula. So crystal field stabilization energy of an octahedral complex I am talking about is equal to the number of electron in T2G level into -4 plus the number of electron in EG level into minus into 6 into plus 6. For example, so before all the d orbitals are degenerated, and after splitting, so T in case of octahedral complex, T2G orbital occupies lower energy and EG orbital occupy higher energy. So here the stability of the complex depends on the number of electrons which is enter into lower orbital. So lower energy orbital. In case of octahedral complexes, the lower energy orbital is T2G. So here if more and more electron comes to this T2G orbitals, more will be the stability. It can be quantitatively calculated using this formula. So and we know that if electron enter into T2G level, it is stabilized by -4 dQ. So this is a SI unit. So it is used to express crystal field stabilization energy. The total crystal field stabilization energy is 10 dQ. So if electron enter into T2G level, it is stabilized by -4 dQ. If electron enter into EG level, higher energy orbital, it is destabilized by 6 dQ of energy. So you must know these things. And dear student, this is a formula which is used to calculate the crystal field stabilization energy. And you know that in order to calculate, you must remember these things. If you just look at the complex, you must able to write the system, whether it is a D1 system, D2 system, D3 system, like that. For example, if there are 5 electrons in the d orbital, it is D5 system. And after identifying the number of electrons in the d orbital, you must able to identify whether it is a strong ligand or weak ligand, because as I said in the beginning, the role of ligand is very important. It decides the nature of the complexes. As I said, the ligand decides magnetic property, color of the coordination complexes and stability. because we studied that there are two types of ligand, strong ligand and weak ligand. The strong ligand force the unpaired electrons to pair up and it is going against the Wundt's rule. But the weak ligand do not disturb anything to the distribution electron in a various atomic orbital. It follow the Wundt's rule fashion. That's why. So one thing, two important thing you must remember. You must identify just by looking the complex in order to identify, in order to calculate crystal field stabilization energy. One is electronic configuration of central metal atom and second one is nature of ligand. So now let us calculate crystal field stabilization energy of various D system. Dear students, if you really understood all the system, so instead of taking a particular coordination complex, I am going to calculate crystal field stabilization energy by taking D1, D2 system like that. So if you take D1 system, only one electron which is present in the d orbital, and in case of a weak field or in case of a weak ligand, so this is the electron is distributed. One electron is present in the orbital and one electron enter into T2g. And in case of a strong field, what happened? One electron which is come to T2g, but the difference is here the energy difference is more, but the energy gap is less. In this case, energy gap is less. Here energy gap will be more. So it can be calculated as, so for both, in case of D1 system, for both weak field and strong field, CFSE is equal to, there are one electron in the T2g, you know the formula. So CFSE is equal to number of electrons in T2g into -4 plus number of electrons in EG into 6. So only one electron in T2g, that's why. So 1 into -4 plus there are no electron in the EG level. You just look at here, no electrons are present, that's why 0 into 6. So CFS is equal to -4 plus 0. So -4 dq. So -4 dq is the CFSE for D1 system. Usually titanium, if you take titanium and titanium complexes, usually they are D1 system. For all the titanium complexes, so -4 dq is the crystal field stabilization energy. Then if you take D2 system, here I am going to explain both in the case of weak field and strong field. You know the meaning of weak ligand or strong ligand. In case of a D2 system, there are two electrons in the d orbital, and after splitting, both electron comes to T2g lower energy orbitals. In case of a strong field, there are two electrons here also. The electronic configuration is same. And the CFSE is, so T2g there are two electrons, that's why 2 into -4 plus 0 into 6 and -8 dq is the CFSE for both the ligand, both in case of weak and strong field in case of a D2 system. So here it is called as D2 because in the d orbital only there are two electrons. Let us take D3. In both the case, so here also there are 3 d electrons and all the 3 enter into T2g orbitals, and here also there are 3 electrons in case of a strong field enter into T2g orbital. The number, as I said, in case of D1, D2, D3 and D8, D7, D9, so the number of unpaired electron, the electronic configuration in the presence of both weak field and strong field, it is same. So here there is no question of high spin and low spin complexes, and CFSE is same irrespective of the ligand in first 3 and last 3 D systems. Okay, and here D3, this is the D3 configuration, and the CFSE here there are 3 electron in T2g, that's why 3 into -4 plus 0 because there are no electron in EG level, that's why it is 0 into 6. So 3 4s are -12 plus 0. So -12 dq is the crystal field stabilization energy of D3 complex. Next, D4. In D4, there are 4 electrons in the orbitals. You know, in case of weak, this is the configuration. This is the splitting in case of weak ligand. in the presence of weak ligand, it follows Wundt's rule. What Wundt's rule says? So during accommodation of electron into various atomic orbital, pairing starts only when all the electrons are singly filled. You please remember this rule. So otherwise you cannot understand the concepts, some of the concepts in coordination chemistry, dear students. So here what happened? There are 4 electron which is present in the ground state or before forming complex. Then after splitting, what happened? Among 4 electron, so 3 electron enter into T2G orbital and 1 goes to EG orbital, that is 1 1 1 1. And again, if it is D5 system, 1 electron comes here. If it D6, so pairing starts from here. So it follows Wundt's rule. So this is the configuration. So let us see in case of a strong field. You just observe here, observe carefully the electronic configuration, dear students. It is not there. So here there are 4 electrons, but all the 4 electrons enter into T2G. Actually, according to Wundt's rule, electrons should go to EG orbital, but in the presence of strong ligand, strong field, so it forces the unpaired electrons to pair up. That's why it doesn't follow Wundt's rule. That's why electron enter into T2G orbitals. So the electronic configuration in this case, T2G3, EG1. In this case, T2G4, EG0. Then let us look at the CFSC of this complex. CFSC is equal to, there are 3 electrons, so 3 into minus 4 plus 1 electron in EG, 1 into 6, it becomes minus 12 plus 6, minus 6 dq, minus 6 dq. Dear students, similarly calculate it for strong field comp ligand. So minus 6 dq is the CFSC for weak field, but for strong field, look at here, strong field, all the 4 electrons present in T2G. That's why, so 4 electron into minus 4 plus 0 into 6, and 4 4 is 16, so 16 dq. You look at the difference. Here it is 6 dq, it is minus 6 dq, here minus 16 dq. That means, so this complex is highly stable compared to this, because it have least energy, less energy compared to this. That's why the one which is having strong ligand, it is highly stable. It is highly stable. So now next I am going to calculate for D5 system.